This is a camera made by 4D Technology. You can see the fraction pattern there. C-mount camera, and so the pixelized pattern is aligned with the CMOS or CCD array in this case, and enables single sensor imaging. People have been making polarized differential polarization cameras for a long time, but they had to be separate cameras. They had a beam splitter block or Clan-Thompson prism or whatever it was to separate out the polarizations. With this camera, alignment is much easier. It's a single camera setup, much more compact than previous technology, and that's part of what my talk is about here. And here's just a really cool example of the kind of imaging that you can do. This is water droplet dynamics from 4D Technology. So here we have a bright field image. This is a time sequence left to right in 100 millisecond intervals. Bright field image from the top of the water, showing the ripple drop entering at this point here. And then the rest of the rows are images from the side, looking down. So here you can see the water droplet entering and spreading. So row B is just a raw interference between the differential polarization image. And the second, row C is process images using a wrapped phase modulo 2N. And the last row is a false color image with a high-low range of about 1.75 waves. So it's really got quite a bit of differential contrast between the two polarization phases. Very cool visualization technique. Reminds me of Schlieren imaging. So there's a lot of other biomedical applications for polarization-sensitive imaging. In tissue imaging, it can aid in seeing subdermal blood vessels for doing optical cancer detection, wound management, polarization microscopy, such as differential interference contrast microscopy, strong advantages involving live and unstained biological samples for increasing contrast, such as a smear from a tissue culture or individual waterborne single-cell organisms. Very easy to see using this kind of contrast microscopy. Biometric facial recognition. Adding difference polarization imaging can be used to detect facial prostheses or even subsurface evidence of facial reconstruction. People that are trying to hide. Polarization difference imaging. Many animals have visual systems that exploit the polarization of light. Some of these systems are thought to compute different signals in parallel from arrays of photoreceptors that are optimally tuned to orthogonal polarizations. But there's research showing that such polarization difference imaging can improve the visibility of objects in scattering media. For example, in dermatology, this technique has been used to record a series of images corresponding to different combinations of illumination and detection polarization. Fitting the polarization difference data to an analytical expression can actually reveal fibrous structure in skin that can be used for the diagnosis of lesions of various kinds of cancers and other skin diseases. And I already mentioned that we were working using fiber optic probes for optical cancer detection. What we were doing was in vivo fiber optic cancer detection using polarized elastic scattering spectroscopy, actually working with Professor Biggio out of the lab here at BU. And that technique is sensitive to changes in subcellular components, namely enlargement of nuclei, enlargement and proliferation of mitochondria, changes in cellular chromatin. So by analyzing the spectra of high-angle reflected photons, we can determine with a flash of light what is now being done with an excisional biopsy preparation of a slide and full histopathology in the lab. Obvious advantage being that we can take an unlimited number of samples, unlike excisional biopsy.